give you an objective to meet that problem statement. Also, I'm going to give you a list of requirements that's been set forth for the design by Evansville Association of the Blind. I'm going to give you a concept of operations, how the tool is going to be implemented in the workplace. I'm then going to give you an overview of my design and show you a demonstration of the prototype from the design, as well as a video of a blind individual using the prototype. Then I'm going to give you a budget as well as a bill of materials for the project, and then hopefully some future plans with Evansville Association of the Blind. So Evansville Association of the Blind is a nonprofit company that employs both blind and disabled individuals, and they've been doing this since 1923. What they do is they accept subcontract work for local, national, and international businesses, and the type of work they perform is production-based jobs that include assembly, sub-assembly of products, packaging, inspection, and reselection of products. Also, they do have numerous programs to teach, rehabilitate, and employ people of various capabilities. Such includes teaching a blind individual how to use a computer, or teaching a blind individual how to more efficiently use their cane for mobility. So one of the production-based jobs that was actually the center of my investigation includes taking a bucket similar to this and actually manually attaching the handles. So if I can come over here, you guys can see it. Basically, an individual that's either blind or disabled, as well as non-disabled, locates the bucket. At this point, they don't have a handle on it. Locates the handle and then locks the handle into place, twists it, and locks the handle into place again. Now, like I said, this is all performed manually, and the average force, depending on the bucket mold, requires 25 pounds of force to actually lock the handle into place. Now, on an average day, an employee will attach 3,000 to 4,000 handles. So, as you can see me do it again, especially if an individual has to overcome some disability, it's very rigorous and tiresome, especially if it's taking 25 pounds of force to actually attach these handles. So, two key items that I want you to be familiar with, because I'm going to use them later in the presentation, is the keyway and the knock. The keyway is the actual location on the mold where the handle locks into, and then the knock is the end of the handle which actually locks into the keyway. Okay, when I was beginning my investigation, I went to the blind individuals in particular, and I asked to see their hands because I wanted to see how they actually were attaching these handles. Also, I was observing that they were using their rotator cuff as well as their bicep to actually produce the force required to actually lock this handle into place. So when I was looking at their hands, I saw that there was some cuts as well as some calluses that had developed from producing so many buckets. And when I asked the individuals, I said, does this affect your mobility at all? And they said, well, at first it did affect our mobility, but we've just gotten used to it. And most individuals will work a 40-hour week. There is some individuals that it is too strenuous for them to actually work a full 40-hour week. So to meet that objective, I wanted to design and implement a pneumatic tool that aids both disabled and non-disabled persons in attaching plastic bucket handles to the buckets that have various size diameters as well as mold thicknesses. Okay, so this is a list of requirements that's been set forth by Evansville Association for the Blind and myself for this design. So the tool shall be usable by the blind and disabled. The tool shall be mobile and under 50 pounds. The tool shall comply with Indiana Occupational Safety and Health Administration standards and regulations. The tool shall accommodate bucket diameters that range from 4 inches to 12 inches. The tool shall accommodate bucket handle lengths that range from 6 inches to 10 inches. And the tool shall be powered by a pneumatic compressor. The tool shall be controlled by hand or foot, depending on the capability of the individual. Some individuals don't have the use of their feet if they're in a wheelchair, so we want to have a hand controller to activate the tool. And for the same reason, the tool shall be usable in a seated position. The tool shall perform a complete operation in a time of 10 seconds, and the budget for the project materials shall be under $900. So here's an illustration of how the tool is going to function in the workplace. At this point, the the user is going to locate the bucket. At this point, it doesn't have a handle. The user is then going to take the bucket, turn it upside down, and place it on the bucket fixture. I'll show you what that is in a little while. The user is then going to place the handle in the correct orientation within the tool, and then the actual attaching is going to take place by the user activating the hand controller or the foot controller to actually do the attaching of the handle to the bucket, and you're going to have your finished product. So here's a SolidWorks drawing of an overview of my design. I have 5 main subcomponents, which I'm going to go into more detail here in a little while. But the 5 main subcomponents are the bucket fixture, the channeled saddle, the air cylinder, and the foot control. As I stated before, the bucket fixture is where the bucket is actually going to be placed to keep it rigid so that they can actually attach the handle. The channeled saddle is where the handle is going to be placed within the tool. And that channeled saddle is going to be actuated in a downward motion by the air cylinder to actually do the attaching of the handle to the bucket. And that's going to be controlled once again by the foot control or the hand control. All right, so the bucket fixture. Basically, this was chosen to improve a pre-existing design that could be adjusted to accommodate the various bucket diameters. The bucket fixture itself, this subcomponent, was actually used previously in production by a one-arm individual, and this design is credited to Rick Engler of the maintenance department. The thing I did add was a circular plate at the top to keep the bucket from actually rotating off the fixture. And then the fixture can be, the bucket fixture can be locked to a specific adjustment depending on what kind of bucket diameters we're running. All right, the frame, it's what I chose for the design is a square shape to prevent any rotation of the saddle. And then the height of the frame can be set to accommodate the user in the seated position. Right now I have this model set at approximately 27 inches, but depending on the user, it will need to be adjusted if they need to be seated once again. All right, the channeled saddle, it's made of a high-dense polymer for durability and to be cost-effective. The saddle is connected to the frame by a square collar bearing. That's to prevent any friction as well as to prevent any wear occurring on the frame itself. Now the cutout allows the force to be distributed evenly, preventing any damage from the handle while it's being attached. Now the air cylinder I chose, it needed to be rated at least 35 psi, 35 pounds of pressure, and the stroke length only needed to be a maximum of 3 inches to accommodate the different handle lengths that we use in production. The pressure and the stroke length can be adjusted by regulators depending on which handle we're using as well as what mold we're using. And the cylinder bore diameter for this chosen model is at half an inch. Okay. I'm going to give you the pros and cons of my design, point out a couple of different aspects of it. The bucket fixture, once again, enables various size diameters and mold sizes to be used. This design also allows more dexterity with the placement of the bucket on the fixture than what they're actually doing currently in their current method of assembly. The tool also eliminates most of the stress on the individual's body. Okay, so as far as the cons, the orientation of the bucket is not yet accounted for in this design. So what I mean by that is it does have accounted for where it will rotate off, but this type of rotation can still occur. And then also the user still has to manually place the handle into the proper location of the tool. Okay. So I'm going to give you some illustrations on my prototype build, and then I will illustrate the actual prototype being used. So here was the pre-existing fixture that was already designed by our maintenance department, Rick Engler. This is where I started off with, is basically just the bucket fixture itself. And then from there I wanted to build the saddle. What I chose again was the durable slip polymer. It's a polyurethane. It was originally a foot long, 2 inches wide, and 2 inches in height, just a square stop. There you can see my measurement marks for where this cutout's going to be, and I'll show you the drilling out process in a little while. That's going to actually do the traveling along the frame. So there was cutting it in two, basically creating two different saddle prototypes that I could use just in case I messed up on the first one. And there's actually drilling out the center hole, which that is what travels along the frame. Now this was a little tricky to actually get the U cut-up shape that I wanted for the saddle. I had to make a jig to fix the actual block stock, and basically there's a hole there. I don't know if you can see it, but I just simply took the stock, placed it in the hole so that I could actually route it out with a tool. So there's the finished prototype, and here it is right here, and I'll demonstrate for you hopefully how to do it. So once again, you take the bucket with no handle, you're going to place it on the fixture, and I'm doing this backwards just for illustration purposes. And then you're going to locate the handle, you're going to rest the knock on top of the keyway, and you slide the handle underneath the saddle itself. At this point, you're not locking the handle in place, you're just resting the knock on top of the keyway. And then hitting the foot actuator, which is then actually attaching the handle. So this is a really exciting part of the whole presentation. I'm really excited to demonstrate this for you. This is an actual prototype test that I did with a blind individual. She is completely blind, and I'll let you make your assumptions from that. So just to give you a summary of what happened in the prototype test, with the current method, the way they're actually doing it now, blind individuals can meet a rate at 2,500 buckets to 3,000 buckets. And with using the prototype, the production rate was 1,900 to 2,100 buckets. Now, however, this was only with 2 days of testing, so the learning curve is yet not accounted for with the test, so more tests need to be done. On a positive note, the individual had no signs of any fatigue in the hand or in the arm, as well as a rotator cuff. And the prototype was tested on a couple other individuals. One individual in particular had arthritis, and prior to using this prototype, she was unable to do any kind of assembly with buckets whatsoever, and she was able to produce similar numbers to the woman that I showed you in the video. Also, another lady that I tested out with just a little bit, she had problems in shaking of her hands, and she was able to complete the operation just as well as the others. Okay, so you can't see too well here, so I put a functional block diagram to show you how it's going to be hooked up in the workplace. Basically, I have the air compressors at Evansville Association for the Blind. It's going to supply 2 lines to the foot controller. The foot controller is going to have one line connecting to a T coupler or Y coupler, depending on whichever one you want to use. And then I have 2 ports, which you can't see the bottom port too well on the air cylinder on here. I have 2 ports on the air cylinder so that I can have a dual actuation, an actuation that's actually pushing the saddle back up after the operation's complete, and one that's actually pushing it down, doing the actual attaching to the handle. All right, so here's a cost analysis of what it took to actually build the prototype, as well as the bill of materials for the prototype. I had my fabrication time for 15 hours total during the fabrication and build, and I rated that at $50 an hour, totaling up to $750. And I have a couple other miscellaneous materials, such as welding rods, nuts and bolts, air hoses, The only other ones that cost to note was the steel material for the tool. That was rated at $40. And then the foot controller being rated at $40, and the pneumatic air cylinder at $20. So it had a total of $887 for the total prototype. Okay, so there are some risks involved for using this tool in production. I'm going to go through the failure modes as well as the precautions taken and the effects that it can cause. So if it's complicated to use, the blind and disabled will simply not be able to use the tool. So to account for that, I made the tool simplistic in function and design. Now, if the bucket does not have proper orientation, production time could increase. And what I did to account for that was add the circular plate at the top from the pre-existing bucket fixture. If the saddle does not have proper orientation, the handle would be difficult to position. And the way I accounted for that in the design was to make it a square, so it would be rigid. As far as the prototype, the way I have it mounted to the air cylinder keeps it from rotating. And also, if a pinch point does occur during operation, obviously an employee would be injured. And the way that I would account for that is the guards would have to be installed to be used in production. Okay, so an overall budget for the project, I have the student time at 20 hours a week for 16 weeks at $15 an hour. That's totaling up to $4,800. Then I have my advisor's time at 1 hour a week for 16 weeks at $100 an hour, totaling up to $1,600. And then for the chosen design, the actual design of the materials were a little bit more expensive, being that the foot controller was at $100, the material for the tool was $100, and then the pneumatic cylinder would be $50, and then the guard material being $25, totaling up to $6,675. As far as future work goes, I would like to do a statistical analysis to compare the times using the current method of production to the production with the pneumatic prototype. I did do some testing, but I need to follow up on that and actually do some more to actually account for the learning curve. I would like to proceed to patent the tool and build multiple tools to be used in production. And then I would like to perform a full-scale cost analysis of the tool, taking an effect the cost of implementation, the cost of material, the usage of air, as well as maintenance and etc. So I do have a lot of people to thank, and kind of bear with me on this one. I'd like to thank Carla Hurl, the Executive Director at Evansville Association for the Blind. I'd also like to thank Tony Gable, who's the Plant Manager at Evansville Association for the Blind. Dan Lieres, Mr. Rick Engler, who's the Head of the Maintenance Department for his pre-existing bucket fixture. I'd like to thank Dr. Mitchell in the Department of Engineering, Ms. Donna Moore. I'd like to give a big thanks to Dr. Kissel for being my advisor and taking time out of his everyday week. I'd like to thank Professor Ellert for his help in SolidWorks. And then finally, I'd like to thank friends and family for everything that you've done. I wouldn't be here if it wasn't for you. Any questions or comments?
All right, questions?
Cody, that was a great presentation. You mentioned taking this further. What do you think is the next biggest challenge in terms of the next step that you would want to do to take this project further?
It would need to have to comply with the OSHA standards and regulations, first of all, to be put in production. I think there needs to be a couple of design changes just so that the cost of fabrication could be at a minimum. I did have the budget for the actual build. I think it can be a lot cheaper, taking in effect that this actual fixture can be changed for time purposes. I used it as well as accommodate different bucket diameters. So it does work, but I think I can change the actual design of the bucket fixture a little bit to eliminate some of the fabrication time, thus eliminating some of the costs that's involved to actually put them in production. But yeah, it would. I would like to proceed to patent the tool, and then possibly I'm going to see about talking to Evansville Association of the Blind's board, seeing what they want to do next step and involvement with that.
So Cody, in the early testing, have you had any indication that the device is pulling too hard, that knocks through the keyway, or I know that was something we had discussed early on as a possible concern. What are you seeing in the early tests?
Okay, as far as the mold sizes and the diameters go, I didn't specify what the actual model number for each bucket was. However, it has a vast range of pressures needed to actually attach the handles. Some of the buckets only require 30 pounds of pressure. These buckets here, as I've taken the handles in and out, are a little easier, but they actually, when they come fresh from our vendor, they actually require about 80 pounds of pressure to actually attach the handle. So a lot more significant than what I thought, and they're actually doing this all manually right now, so that gives you an idea. It's kind of like taking a dumbbell and doing this 4,000 times a day, attaching the handles. So it's very rigorous and tiresome.
But you're not seeing any damage between the knob
Oh, I'm
and the
sorry.
keyway?
Well, yeah, you have to adjust, like I said, they have to have the regulators to adjust the pressure.
Okay.
Otherwise, you're ripping out the keyway in some of the lighter models.
Mhm.
These can't get much more than 80 PSI on them, but I haven't had any problem actually tearing up the keyways on this model.
Great job, Cody. Great job, Cody. Good project. Great job, Cody. Good project. You had a second video.
Yeah.
Do you want to share that with us?
Sure, I'll show it to you. It's zoomed in a little bit more on the saddle. It's the same lady, just because she had given the permission to actually illustrate her doing it. So I can show you that.
Did the ladies seem to like it?
Yeah, in my report, I gave some specific quotes. As far as the 3 individuals that I tested with, the lady that's illustrating this video, she really liked it. She said it took all the fatigue basically out of the production, which was the main goal in the beginning, to eliminate all that stress put in the individual's body. She said that it was a little slow at first, but she was blind and she had to get over somewhat of a learning curve. And she did approximately 2 days of production, and that was at 12 o'clock, starting at 12 o'clock. So really, maybe a 16-hour period total that she actually got to use the tool. But I think that learning curve after she gets over that should be a lot faster. But especially for like these type of buckets, because the force required to actually lock the handle into place is a lot more. She really particularly liked it for these, especially the other individual that wasn't able to do the bucket production at all. She could do any of them, so she really liked it. Her quotes was that it was rad and it was awesome, and so she really liked it. And she was a hard critic too, but she gave nothing but positive feedback on it. Thankfully, so.
That really added to the presentation to have the video.
Yeah, I should have just did that and summed up everything.
Donna beat me to my question.
Oh.
But I did have another one to follow on was you talk about the force, are you talking about the force to pull the knock into the key
Yeah.
or the air pressure?
As far as regarding.
What you mentioned, 30 pounds.
Yeah, the current method, it's depending on the mold or the bucket diameter, it's 35 pounds to actually pull it into place. And then now, for the actual actuation of the tool here, I've had to turn it up to 80 pounds of pressure. For this bucket, yeah, PSI. Yes. I gotta get that terminology right. PS. And then as little as 30 pounds of PSI. That answers your question.
All right, other questions? How many of these would they need if they were to fully implement?
That's something that still needs to be discussed. As far as blind individuals, it ranges from 25 people, depending on what production day there is. As far as other people who have disabilities and non-disabled, it could be a total of around 45 tools that would need to be implemented. And if we made one available for somebody, it would have to be available for another person. But that's still yet to be discussed with that association.
Okay. Other questions? All right, let's give them a hand.